Welcome to the 19th Andrew Chamblin Memorial Lecture. My name is Harvey Rial. I'm a professor here in the Department of Applied Mathematics and Theoretical Physics here at the University of Cambridge. Before I introduce our speaker, I'll start by saying a few words about Andrew Chamblin. So Andrew was born in Lubbock, Texas, and brought up in nearby Amarillo. After a brilliant undergraduate career at Rice University, he moved to the UK to study for a year in Oxford, where he worked on twistor theory with Roger Penrose. He then moved here to Cambridge to study for a PhD under the supervision of Gary Gibbons and Stephen Hawking. He was subsequently elected to a junior research fellowship at Pembroke College here in Cambridge, and he held postdoctoral positions at several institutions before going on to become a professor at the University of Louisville in Kentucky. Andrew wrote many influential papers on general relativity and quantum gravity, including one which now has 1,500 citations. Sadly, Andrew died unexpectedly in 2006 at the age of just 36. Following his death, his friends and family established this lecture series in his memory. The first Andrew Chamblin lecture was given by Stephen Hawking, and he was followed by many more very distinguished speakers. You can find recordings of nearly all of the talks on our website. So, now to today's talk. First, a couple of practical points. There are plenty more seats at the front rather than standing at the back. There are some besides. If you want to ask the speaker a question, then there'll be plenty of time to do that at the end. So, unless there's some urgent clarification that's required, it's best to avoid interrupting during the lecture. So, let me now introduce our speaker. Thibault Damour studied at the École Normale Supérieure in Paris and received his PhD in 1974. After a fellowship in Princeton, he took up a permanent CNRS position in Paris. He was appointed to a permanent professorship at the Institut des Hautes Etudes Scientifiques in 1989. In his research, Thibault has made many fundamental contributions to our understanding of the gravitational force. His work plays a key role in decoding the gravitational waves detected by the LIGO Virga-Cagra detectors. His work has earned him numerous prestigious prizes, including the Gold Medal of the CNRS, the Balzan Prize, the Dirac Medal, the Einstein Medal, and the Breakthrough Prize in Fundamental Physics. Please join me in welcoming Thibault to deliver the Andrew Chamblin Lecture this evening.
Okay, so thank you. I'm honored to be here. I was struck by the range of topics and interests of Andrew Chamblin, especially his love of music, because I'm also a musician. Okay, so today I want to give an overview of several topics in general relativity, from gravitational waves, black holes, and going to experimental tests of gravity. So our story starts during the war, the First World War, while some of the colleagues of Einstein were busy invented very dangerous gases, some of his very close friends, Fritz Haber. Einstein closed up, and although Max Planck was not at all happy that he would concentrate on gravity, saying it's not an urgent problem at all, quantum mechanics is a really important problem, he worked very hard for years. Here you see on the left his hand calculations around 1912, where he rediscovered many things that had been forgotten, okay, like the Bianchi identities and things like that. And then in November 1915, he gave us these equations, okay. An explicit form of Einstein's field equations is written here. So they are both nonlinear, somewhat complicated, but not overly complicated in a sense. They are more complicated PDEs, as Harvey would know. And let me describe in just a few words one way to understand intuitively the meaning, the basic message of Einstein's theory of general relativity. The basic message is telling us that space-time, or space, depending how you see it, is an elastic structure which is deformed by the presence within space and time of energy and stress. So essentially, in one image, so space, which before Einstein was a rigid structure described by geometrical laws of universal validity independent of space, time, and the presence of matter, now becomes this like a jelly. And I would like, although I tried to find a connection between Robert Hooke and Cambridge, I must say I found only a connection with Oxford and London, but nothing. But as you will see, I was struck while preparing this lecture to see how many people from Cambridge created absolutely fundamental contribution to gravity, to my topic. But the first one I want to mention is Robert Hooke. Okay, so Hooke was the first one to understand that if you have an elastic medium and you submit it to some stress, then it gives a deformation, and in first approximation, the deformation is proportional to the stress, okay? So we can view Einstein's equations as saying that the stress, because it's really the right-hand side contains really the stresses, like if you have stresses in some material body, creates a deformation of the geometry of space, okay? And that in between there is a coefficient, the inverse stiffness here, and the fact that this inverse stiffness is given by Newton's constant divided by the fourth power of the velocity of light means that the inverse stiffness is very small in ordinary units, which means space is extremely stiff. Even when you submit it to very large stresses, it is extremely small. I mean, you say the deformation is extremely small. Now, at the linear level, when you look at Einstein's equation, you can say two simple things. If you take, for instance, a triangle, we know that the Greeks told us that the sum of the angles of a triangle are equal to pi, okay, or 180 degrees. Einstein says that if within the triangle you put the maximum mass you can, some dense object which just fits within the triangle with mass m and radius r, then the sum of the angles is no longer equal to pi, but slightly larger by a quantity which contains this small coefficient here, okay, and which is g times the mass divided by the radius and the square of the velocity of light, which is usually in many conditions very small, except when you go to strong gravitational fields, as we will describe black holes. Another consequence is if you have any elastic medium and you start, creating perturbation in them, then there are waves of deformation that propagate in the medium, and therefore you expect that there should be, in the jelly-type space, waves of deformation, which are called precisely gravitational waves. And indeed, in one so it was in November 1915 that Einstein finalized his theory. And then a few months later, in 1916, he studied linearized perturbations, linearized deformation of the geometry of space-time. He wrote down some equations and then could solve them and found what we call now gravitational waves at the linear level. And the essential characteristics that he got is that gravitational waves, like electromagnetic waves, contain two different polarizations, okay? Although his first papers, he got three polarization actually, for some reasons that we quickly allude to, and that he also said that any moving distribution of masses where the quadrupole moment of this mass distribution varies would generate some wave that would propagate essentially at the velocity of light from the source and decay like 1 over r. We will talk about these waves, but before this, one of the main points of this talk is to remind us that some of the important concepts of general relativity that you can take for granted now took many years to be grasped, to be understood in detail, to be believed in, and finally to be measured, because Einstein wrote his equation in 1915, and the first direct detection of a gravitational wave passing on Earth was done in 2015, precisely, exactly 100 years after that. And it was not only because of technological reasons that it's difficult, but also conceptual reasons. And this is what I want to explain. In particular, yes, so actually this is from the first paper of 1916 of Einstein, which says the amount of energy per second emitted by a system of moving masses. And this formula is wrong because it says that that the gravitational waves have not only two polarizations, but also a third one, okay, that he understood 2 years later that this was a gauge effect. The gauge effect means that in general relativity, you have to distinguish between what is really physical and what is an effect of changing the coordinates, the way to represent how space is described. And also in this first paper, there is this sentence, I mean this thing saying praktisch verschwindenden, which means that he's saying if you put numbers, because the stiffness of space is so large, if you try to excite waves in this system, they are extremely small, okay? And he says practically vanishing, okay? And this is something which remained for many, many years, because when I was a kid in 1968, and I read Landau-Lifshitz treatise on general relativity, there was a sentence written explicitly, I have checked, saying that even for binary systems moving on cosmic times, the amount of energy lost in the form of gravitational waves is so small that it's totally negligible. Okay, and actually it is not, as we will see. Now, but what is remarkable is in the same paper of 1916, Einstein says, maybe gravitational waves emitted by binary systems, including an electron moving around the nucleus of an hydrogen atom, maybe it's negligible quantitatively, but conceptually it's very important because it means that we must change quantum mechanics or modify quantum mechanics, because at this stage you expected that there was no radiation of electromagnetic type in a quantum atom, but if gravity is a new source of radiation, what about this? Anyway, beyond the linear level, people worried about it, starting with Eddington in 1922, saying Einstein had derived the existence of gravitational waves in a linear effects, but if you have a system of two masses going around, you need to take into account nonlinear effects. Sometimes people say that Einstein, Rosen in 1936, said something totally stupid by publishing a paper saying, do gravitational waves exist? But actually, Einstein was posing a deep mathematical question that if you have a system of nonlinear equations and you find a solution of the first order linearized equations, it does not prove at all that there exists an exact solution whose linearized approximation is equal to this. There are counterexamples. There are cases of PDEs that admit no such solutions as wave of this type. So Einstein was asking real subtle questions because of global nonlinear effects. For years, many physicists had doubt about the existence of gravitational waves. There was the problem of boundary conditions. Should we use something different from the past and the future, retarded, time symmetric? How can you characterize the gravitational waves? And if they are so small, how can they be even detected? So I just want to mention that although many people contributed, there are three pioneers that I want briefly of gravitational waves that have established our modern idea that gravitational waves exist in Einstein's theory. In particular, Madame Yvonne Choquet-Bruat, in her thesis in 1951, proved, this is written in French, sorry, but proves that there exist waves and gravitational rays, and there is propagation phenomena and things like that. So it's And this was in 1951, at a time where many other physicists, including in England and in America, were confused, said maybe they don't exist, do they exist? But she had proven that they existed mathematically without any doubt. The second person I want to highlight is Joe Weber, and I want to mention something that I learned by personal discussion with Joe Weber in 1975 at a moment where he was ostracized by everybody because nobody could confirm that what he had claimed to detect. He had claimed to detect gravitational waves, that this was probably a wrong effect, that's what he had seen. So he was alone and he talked to me and he told me that he learned, he realized that he could in principle detect gravitational waves by discussions with a mathematician, Marcel Ries, actually. And then he understood that if you have a cylinder, a big metallic cylinder, when a gravitational wave passes, the intuitive idea that I said at the beginning that gravitational waves is a wave of deformation of this elastic medium, which is space, and a cylinder which is put in space, so when space vibrates, the cylinder will also vibrate, and you will have a relative change of the length of the cylinder proportional to the intensity of the emitted gravitational waves, okay? And he was the first one to have the idea it was something you could detect in principle. I want also to mention, because this is not well known, that the first one who understood that Landau-Lifshitz was wrong about binary system, or at least you need to complete what they were saying, was Freeman Dyson. Freeman Dyson is one of the very important physicists of quantum field theory and many other things of the 20th century. And he studied in Cambridge, and his last book is very interesting to read, which is a Maker of Patterns, autobiography by letters. Okay, there are many things about Cambridge at the time of Hardy and others. Okay. Anyway, the point of Freeman was the following. That will give you also the basic ideas that I'm talking about. Now we consider a binary system of two compact stars, and this was in 1963, where nobody in the world believed that there could exist very compact dead stars, neutron stars, okay? At the time, nobody talked about black holes as being really formed from collapse, but neutron stars, he believed in them, and he said, if I have a binary system made of two neutron stars, it is true, as Landau-Lifshitz says, that for many years, they have a Newtonian binding energy, okay, kinetic plus binding energy. They lose energy according to the formula I've written of Einstein improved by Landau-Lifshitz. So you compute the loss of energy of this system in the forms of waves at infinity. You write that the loss of energy of the system is equal to what is lost at infinity, okay, with a minus sign. And then you find that the two bodies, they get closer and closer by a very small amount for millions and millions of years. But if you wait millions and millions of years, if you think of the time scales, you know, the universe exists for a long time, then they will get closer, 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 closer. And he writes explicitly that at the end, they will they will go extremely fast at half the velocity of light and will emit a flash of gravitational waves of an unimaginable intensity, okay? And he gave us a challenge of saying, and then he adds, and one should have detectors of the type introduced by Joe Weber to measure this event. So he was the one to have the vision that indeed for millions of years, binary systems emit nearly nothing, but at the end, when the two compact stars get very close, they go fast and they emit really an enormous amount of gravitational waves, and this is, as we will see, that what we have detected, okay? I should also mention the name of Ray Weiss, who died recently, and who was the first one to prove that you could detect these waves, not by using, like Joe Weber, a vibrating bar, but an interferometer, okay, interferometric. Now, this was the first part on gravitational waves. So gravitational waves in the theory were introduced in 1916, but it took a very long time to understand they could exist, they could be detected in nature. Black holes also, it took a very long time to grasp their meaning and think they could be real objects. And I will go through a little bit through the history. Here you have just a gallery of pictures. Let me just say the name. So this is Schwarzschild, this is Oppenheimer, this is Tullio Regge, John Wheeler, Roy Kerr from Cambridge. I mean, he studied in Cambridge. Zeldovich, okay, Novikov, Roger Penrose, sorry, from Oxford, Lyndon Bell, we are back to Cambridge, no? Vishveshvara, Christodoulou, Remo Ruffini, and then, evidently, Stephen Hawking and Gary Gibbons, who is here in the audience. Just to show that, as historians of science, emphasize, a theory is not, defined the day the fundamental equations are written. It takes many people, many brains, many ideas to take out from these fundamental equations the real thing they contain. So our story of black holes starts just like 2 weeks after Einstein writes his equations. When Einstein writes his equations, he sends the proofs, which was the only kind of copies you could make at the time of his paper before publication, to a colleague. The colleague was actually on the east front because we are in the First War, and Germany is at war with a lot of Europe, and Schwarzschild is on the Ukrainian front, okay? But the Ukrainian front is not very active, okay? So he has the time to get the first exact solution of Einstein's equation. This is his paper. And then, although he solves Einstein's equation in a way which is not what you find in textbooks, at the end he writes this. So he says, this is an exact solution of an isolated mass point in general relativity. The analog of what in Newton's theory would be to say, I put a mass concentrated in a very small region of space, and then it generates a gravitational field in 1 over r square around as a field, or potential in 1 over r, okay? This is an exact solution of Einstein's equation. But then, immediately, people notice that this equation has strange features. There is here something divided by something, and then when the distance away from the center in this solution is equal to this number, where m is the mass of the object, like the sun, this gives 1 over 0, which is infinite, and here it becomes 0. So for many, many years, people said, it is a singularity, and we don't know what to do with this, okay? There were discussions in Paris in 1922. So for a long time, this was something obscure. Why it took so long? Why it took so long? Also because it took, again, many people here from Cambridge, okay? So you have Eddington, Chandra Sekhar, Roy Kerr, Lyndon Bell, the discoverer of pulsars here, and here Giacconi and Gursky. Okay, it took so long because it took people to realize that stars evolve, that they burn their nuclear fuel. They then Fowler, probably from Cambridge also, Chandra discovered that stars at the end of their evolution cannot have an arbitrarily high mass. There is a maximum mass. Then Oppenheimer in 1939 understood that for neutron stars, this maximum mass is not very high and much smaller than the mass of many stars we see. And therefore, he considered for the first time that maybe if you exceed for a dead star this mass, something will happen. And this was the beginning of black holes. And then pulsars were discovered experimentally, et cetera, et cetera. So just to say that it's a conjunction of conceptual developments, experimental facts. That's why it took many, many years to transform this strange Schwarzschild singularity. And by the way, there is a strange historical fact that the name Schwarzschild means black shield, okay, which is nearly what is a black hole. Okay, it's an accident. And so the crucial work was the one of Oppenheimer and Snyder in 1939. But because of the Second War, actually, it took years for this work to have an impact. And also what is strange, I asked several times Freeman Dyson, Oppenheimer probably never realized the importance of what he had done. He never discussed with people in Princeton that maybe this was an important problem to investigate. He never discussed with Einstein, actually, about this, or anybody. It was the Russian school in the 60s that took up concept from a physical point of view, this idea that maybe there is something real. So let me repeat, what Oppenheimer and Snyder said was that if I have a neutron star, a dead star, which has reached its maximum mass, and then I add a little bit of matter, I add a few neutrons, then it exceeds the maximum mass it can have, and then what happened? Gravity becomes stronger, and therefore it should contract. It should collapse on itself. And then what happens? It was a bit mysterious. They said the Schwarzschild singularity appears, but this was unclear. The Russians understood better, but finally the full geometrical picture was understood by Roger Penrose, saying that there is, I will not describe this in detail, but there is a region of space-time in which two things happen, where a black hole is created, a region of space-time out of which light cannot emit. If you remember what I said at the beginning, that Einstein's theory can be summarized as a nonlinear Hooke's law of the elasticity of space, you can say that around a star, so the star which collapses is there. This is, sorry, it's written in French here. You have a star, time goes up and space is horizontal, and the fact that this goes like that means the star is getting smaller and smaller. In this region of space-time, the elastic space has attained its plasticity limit. You know that if you have an elastic medium, if you try to stretch it a little bit, like it comes back. Okay, it's linear elasticity. But if you put too much stress, it will never come back exactly to the shape at the beginning. This is what happens in a black hole. Black hole is a region of space where space has been deformed permanently in space, and you have a region out of which light cannot escape. But then there is more. Inside the black hole, what happens is you go to the second limit of an elastic medium, if you have an elastic medium, and then if you start putting too much force, it will break. And then, and this is what happens inside the black hole. In the middle here, there is a tearing of space-time, the rupture of the elastic space, and you have a big crunch. Okay, this picture was first understood by Roger Penrose. Now, but still, at this stage, black holes were a mathematical object. One had understood that they might be created by the collapse of a star, but one was far from the full understanding. And an important breakthrough paper was by Tullio Regge and John Wheeler, where they show for the first time that you can take a black hole and, in a sense, perturb it by putting some waves, like if you have an object and you touch it from outside, and they are saying it will vibrate, but come back to its original shape after a while. So it was the first paper in '57 where black holes are not understood. It's before Roger Penrose and before the Russians, okay? But it makes this strange mathematical object of Schwarzschild like a physical object, okay? Then a very important discovery is by Roy Kerr, where he finds a more complicated version. You remember on the previous slide, I had a solution which was very simple. Here you have something complicated, which was discovered by strange mathematical arguments, but now which is considered to represent what happens to a black hole when you make it rotate on itself. which means that when a star was rotating and collapses on itself, it's supposed to create this object, this curved spacetime. Another very important result is by Vijayeshvara, who was the first one to understand that if you have this strange object, which now is called black hole because we are in 1970, and if you send an arbitrary type of waves on it, there will be characteristic modes of damped modes of vibration of the black hole created by this perturbation, okay? That a black hole is like a bell, and if you strike a bell, then it emits some characteristic modes of vibration of the bell which decay in time, okay? So this was understood in 1970. Then another important thing linked to the work of these people is the fact that black holes contain a lot of energy that you can extract. They are not only a region of space where things only fall inside and cannot come out. There is a lot of energy, for instance, rotational energy, that you can extract if you deal with them in special way, an enormous quantity of energy, okay? And also that when you try to extract energy from a black hole, there is a quantity which always augments, always increases. And early on, people said, when in physics there is a quantity which can never decrease or increase, but only increase, it reminds us of the second law of thermodynamics, that there is something irreversible, and that the entropy of a general closed system always increases. And this understanding has been improved by Bardia. This is Brandon Carter here, and others. And then it was understood that black holes also have an electric resistivity of 377 ohm surface velocity, that they have a certain viscosity and things like that. So more and more it was understood that black holes should be considered like ordinary physical objects. Okay, this ends the part where I was saying it took many years for the concept of gravitational waves to be mathematically believed in, and then physically saying maybe we can detect them, maybe there are systems like binary systems that at the end will emit sufficiently to see them. Then I said that black holes that were just a strange solution, little by little people said maybe they exist in the universe. Now, what is the first experimental proof we had that gravitational waves exist, which means that gravity propagates at the velocity of light? This was obtained by the discovery of the binary pulsar, the first binary pulsar by Hautes and Taylor. And Joe Taylor announced, I remember I was there in December of 1978 at the meeting in Munich, Texas meeting, where he announced that he had seen a small variation of the orbital period. So a binary pulsar is made of two neutron stars going around. In this system, the two neutron stars, they go around at 1,000 the velocity of light, which is both small but still quite not so negligible, okay? And the orbital period is 8 hours, okay? I also remember, for you as a warning, the first paper that I wrote in my life, actually it's the second one, but it's the first published, in December 1974. I had done calculations with Remo Ruffini on the binary pulsars, but I was influenced by what I had read in Landau-Lifshitz, saying gravitational waves are so small that it's as if they were negligible. And in it, I had computed the loss of energy in this system, and I said, oh, it's so small in ergs per second that it will not be important in the evolution of the system. But we predicted another effect, which is that each pulsar is a gyroscope, and therefore it should precess, and we should see that. And this has been seen 20 years later also. And now we know that this system will disappear in a few years because of this. But anyway, I was proven wrong by Taylor, because after 4 years, he has seen indeed the fact that the orbital period is changing. So this is the accumulated shift of the orbital phase, okay? Orbital phase is where you are in the orbit, If the orbit changed, you go faster and faster. And the orbital phase, you have this negative sign, which is saying that the orbital period shrinks, gets smaller and smaller. And this is what is predicted by GR. So you see, already at the beginning, there was an agreement in 1980 between GR and this, and over the years, it's better and better. And with Nathalie Deriel, who worked a lot here in Cambridge, we had shown that this is indeed a sharp prediction of the fact that the gravitational force acting on this pulsar due to its companion has propagated at the velocity of light in a retarded manner and with nonlinear effects predicted by GR. Okay. So it's a direct proof that gravitational radiation exists. But not a direct proof that we have seen gravitational waves, because here you see that the waves has propagated between a neutron star and its companion within the system, okay? Now, it's only on 14 September 2015 that the two LIGO interferometers, so these are 4-kilometer, two arms of 4 kilometers containing laser light which bounces between a mirror in the central building here and mirrors at the end. They go back and forth. And then when a gravitational wave passes, so as I said, the wave is a wave of vibration of space. So you have light between two mirrors, and if space vibrates, the mirrors which are put in space will also change their distance, and therefore the laser light will have a different phase when it bounces, and then you see this in interferometric fringe, okay? And but let me see exactly, yes. So the first detection by LIGO has been quickly interpreted as, by analyzing the data, and I will discuss how the data look, you can deduce from the data that this was a system of two objects having 36 times the mass of the sun or 29 the mass of the sun, located extremely compact and located 1 billion light years away, so really far. And these two objects, the system caught them at the last few orbits before these two things interpreted as black holes, and I will explain in what sense we have proven they are black holes, merge at the end. But let me show you the real data. In general, when people do not show what were the real data seen by LIGO, these are the real data seen by around the 0.2 seconds around the event. Yeah, because these gravitational waves, it took 1 billion years to travel from far away on the Earth, and then it crossed the Earth in 0.2 seconds, okay, like that. The full signal, okay, lasts only 0.2 seconds. And here you can see what you measure in LIGO, which is the fractional change of those big arms, the distance between the mirrors, 4 kilometers in this direction, 4 kilometers in this direction. And you can see that the two arms, they do indeed vibrate like this. But if you look at the scale here, you find that this fractional change is of the order of 10⁻18, okay? But the real gravitational waves was 10⁻21. So what you see here is noise, broadband noise. It's not at all the gravitational wave. The gravitational waves is 1,000 times smaller than what you see here. So the gravitational waves is something extremely small, which is totally lost in the noise. And this is even more true for other detections later, okay? Like all of these, the gravitational waves, which passes in the system, is 1,000 times smaller than what you measure really. So how could you conclude from this very noisy signal that you have seen a gravitational waves which is not of the order of 10⁻18 as a fractional variation of the two arms, but 10 to the minus 21? You do it only if you know the shape of the signal, because it's like if you look for a needle in a haystack. If you have no idea of the shape of the needle, of its size, of its color, of the metal it is made of, you will never find it. Why? If you know very precisely what type of metal, what type of shape, then you have a good starting point for looking for this very small object, okay? This is, and this is the way it is, it has been measured. Like, actually, it has been measured by combining several things. I will not describe the details. I will just remind you that with Alessandra Buonanno, who was my postdoc at IHES, we had computed by purely analytical means what should be the gravitational wave signal emitted by the last orbit and the coalescence of two black holes. You can imagine that two black holes are like two bubbles, soap bubbles, you know, and if you have two soap bubbles, if they are far apart, they look like two small points, but when they get very near, if they start touching, then the two soap bubbles will coalesce together and make one soap bubble. And then, using some approximation linked to various things, including Vishveshvara prediction of QNMs, we predicted what was the full signal. Nobody believed this at the time, especially in America, where numerical relativity had been developed for 30 years, but then without explicit results. And it took 5, 6, and 7 more years until the breakthrough of Franz Pretorius and another breakthrough of Manuela Campanelli, Carlos Lusto, and John Baker in America to compute on a supercomputer what was the process of the coalescence of two black holes. And then they could find gravitational waves that were compatible with this. And then by mixing the two, one can improve the prediction. So I will not spend much time on this, but just to say that starting from Einstein's equations, so you have these equations from 1915, you want to solve them now for this complicated problem, which is you have two black holes created by the collapse of stars in the past, and you want to see what happens over the hundreds of millions of years where the two black holes go around each other. So this diagram, I've not explained what it is. This diagram is a space-time diagram where you represent space as being the vertical dimension, time as the vertical dimension, and space as the two horizontal dimensions. We cannot represent the three horizontal space dimensions in space, so you forget about one dimension of space. You say that space is only what happens, let's say, on this surface. There are two dimensions of space, and then you have time. So it gives you a three-dimensional picture. And then a black hole is represented as a tube. The motion of two black holes around each other is like two tubes twisted around each other. They emit gravitational waves for a very long time. They get closer and closer by the argument of Dyson. And then at the end, they coalesce and they form one final black hole with some ripples on it. And then this emits gravitational waves at infinity. And there are equations for this, okay? I will not mention the equations, just that actually, analytically, you can generalize an idea discovered by Newton that the two-body problem in Newtonian gravity is equivalent to one body with some effective mass moving in the potential created by the interaction between the two bodies. And then you can write what is the motion of the two black holes around each other, what gravitational waves they emit. You need to introduce a lot of technical details, resummations of infinite number of leading lobes and things like that. I will not enter into detail. If somebody is interested in details tomorrow afternoon, I will give a talk about the details. Anyway, the last part of this survey of general relativity and its connection with the real world is a summary of what are the experimental evidence we have that Einstein's theory of gravity is the good theory of gravity. Pace Isaac. Einstein's theory is based on several assumptions and structures. And one of the basic ideas of general relativity is to take seriously what Galileo had understood, and actually other people before Galileo, that if you take two bodies of different mass and different composition, like actually Galileo proved that if you take 10 kilograms of lead, it falls like 1 kilogram of lead. Okay, so it's surprising for most people that a very heavy body can fall like a light body, but Galileo had understood it's easy to prove that 2 kilograms of lead fall like 1 kilogram, because you take 2 kilograms of lead and then you attach them with a small string, and then they will fall like each 1 kilogram separately. But what is surprising is 1 kilogram of lead is following like 1 kilogram of stone or copper or water or whatever, okay? And the fact that all bodies fall exactly with the same accelerations has been verified in a recent space experiment just from 2-3 years ago at the 10⁻15 level, okay? So now we have verified at the 15th digit that the fundamental postulate of Einstein's theory is correct, and it is also checked at the 10⁻14 level in lunar laser ranging experiment. I will not discuss the other thing. I jumped to, I think. Yes. Now, you can also test whether Einstein's theory gives good prediction, let's say in the solar system, in regions of space and time where the deformations of the structure of the geometry by the sun and by the planets is small, okay, of the order of 10⁻6, 10⁻8. This is something that Eddington had parameterized. Eddington in 1922 had said that maybe Einstein's description of the solar system, which is given by this formula, might not be correct. And he said maybe there is a different theory where instead of a coefficient 1 here, you put a beta, and instead of a coefficient 1 here, you put a gamma. So in general relativity, the two Eddington parameters, beta and gamma, are 1. And Eddington thought, okay, maybe there are different theories of gravity. Now the latest data are saying that gamma bar, which means gamma -1, so it's the difference of gamma to 1, is smaller than 10⁻5. And beta -1 is also smaller than, let's say, 10⁻4. So we know that in the solar system, Einstein's theory is an excellent description of gravity to 10 parts in a million, let us say. Okay. Now, I said that Hautes and Taylor discovered the first binary pulsar, and this binary pulsar gave us the first proof that gravitational radiation exists and propagates at the velocity of light. Actually, binary pulsars give us the strongest test, the most accurate test that general relativity is valid even for strong fields and for time-varying radiative fields. Why strong fields? Because a neutron star is such a compact object, is nearly as compact as a black hole. You remember that in one of my first slides, I was saying that if you put an object of mass m and radius r in the middle of a triangle, the sum of the angles of the triangle will differ from pi by a factor 2gm over c square r. For neutron stars, this difference is already 60%, okay? And for a black hole, it would be 100%. So a neutron star is nearly as strong a deformation of the geometry of space as a black hole. And in a binary pulsar, you have two neutron stars, and therefore the effects that you observe from the Earth depend on the strong field nature of the sources. And here I'm just citing recent numbers. First, in this original binary pulsar, the agreement between the observed change of orbital period and the one predicted by general relativity agrees to the, you see, 2% level, let's say, if I take the average here. By the way, I remember here there is a correcting term. I also remember one day after the announcement, years after the announcement of Joe Taylor, one day I got an email from Joe saying, Thibault, we have a problem because the observed value of the orbital period starts differing by 3 sigma from the predicted value. Okay. But then with Joe, we discovered that there was a classical Newtonian effect that you had to take into account. And when you subtract this effect, the agreement now is 1%. But even more impressive, there is this system called the double pulsar, or double binary pulsar. This double binary pulsar is a binary pulsar where each object is a pulsar. In most of the binary pulsar, a pulsar, so like Jocelyn Bell discovered, is something that rotates and which emits a beam of radio waves. And when you see at each turn the radio wave, you have something in your eye like a lighthouse, okay? A double binary pulsar is a system where each one is a pulsar that you see by accident, because it could be in all directions. Although actually, so it is a system where you have 2 beams, and for a few years you saw the 2 beams. Actually now you see only 1 beam because of the effect I was saying at the beginning, which I predicted in my first paper, which is that they should rotate away and you don't see them. And then it's one case where you see them. But what is beautiful is that in this system, you measure 7 independent parameters, which are function of only 2 unknown physical characteristics of the system, which is the mass of the pulsar and the mass of the second pulsar, M1 and M2. And if you measure 7 functions of 2 parameters, it means that in the xy plane, where the x-axis is the first mass and the y-axis is the second mass, you have 7 curves. Now, if general relativity is the correct description of gravity, and the curves predicted by general relativity for each observable, they should meet only at one point, which is the 2 masses, the correct physical masses of this. And here you see that the 7 curves meet at one point. So it is a case where we have 5 accurate tests of the validity of Einstein's theory in the strong field and radiative domain. And here I have cited the 2 best tests, okay? There is a test of radiative gravity, which is, you see, at this accuracy, this is 1 plus this, and there is a test of strong field gravity, which is not radiative, which is valid at this accuracy. So it's extremely impressive, and people who talk about modified theory of gravity have the duty of checking whether binary pulsars agree with their theories. Now, so as I said, starting in 2015, LIGO detected the first gravitational waves coming on Earth. And I want to, as of now, LIGO, then completed by observations of the French, Italian, European detector Virgo, and of the Japanese detector Kagra, has detected over 300 such events. Most of these events are the coalescence of 2 black holes. A few of them, it's written probably on the next, yes. A few of them are the coalescence of 2 neutron stars, the ones that Dyson was talking about, and 3 of them is probably the coalescence of 1 neutron star and a black hole, okay? But most of them are binary black holes, and this diagram shows all the masses of these binary black holes, with surprising facts that there are black holes of masses 60 and 70 that coalesce together to make a black hole more than 100 solar masses. So there are many surprises, okay? People did not expect such large masses. Let me just mention to end what are the most impressive confirmations of the validity of Einstein's theory obtained by all the detections of LIGO, Virgo, Kagra. One important test is the fact that the velocity of propagation of gravity, of gravitational waves, between the system and us agrees with the velocity of propagation of light, because in this system you could see both electromagnetic signals, this system GW 170817, you could see both electromagnetic signals and gravitational waves coming from the same system, and this is, very far away, so you can see the velocity of propagation difference. The two velocities agree at the time minus 15 level, okay? Another thing is, I will not describe here, but in Einstein's theory, there are many subtle effects. Gravitational waves propagate not in flat space-time, but in the space-time curved by the mass of the system, and this delays the waves. This is called a tail effect, and the tail effect has been verified at the 3% level by this. Okay, so this is important. And now I want to talk about a very recent discovery. I mean, the discovery, this system is called GW 250114, which means it is the gravitational wave event detected in January 2025. It's the 14th of January 2025. Why is this event especially important? Not only because it is 10 years after the first event, but because this is the system with the highest signal-to-noise ratio ever seen by LIGO. It has a signal-to-noise ratio of 80, which is enormous in this business. Before, the highest signal-to-noise ratios was 24, 27, something like that. 80 is a big difference. Now, this is, actually, these are whitened data. So here, the real data, after whitening means taking away the noise by the inverse noise. So the data are these gray things here, okay? This is this thing. And what you see here, the curve that you see here and here are theoretically computed expected signals. So they are there just to guide the eye. Actually, one should take them away to see the real thing. But at least you can see that indeed the real signal is, although it is fluctuating, okay, with high noise, is around the real thing. And it is so much around that the signal-to-noise ratio is very high. Now, this system has so much signal-to-noise ratio that you can do many things with it, okay? And in particular, what you can do is you say, even if I forget about this part of the signal which is created when the two black holes really coalesce, and I use a kind of secure knowledge from perturbative knowledge of computing general relativity from these cycles, that is to say, this part of the gravitational waves is due to the fact that the two black holes are still a little bit far apart, okay? They are at 4 times the radius. They go around, and they go around for a few times. So if you use this part to say, I still don't know what will happen at the merger, but I can extract the masses of the two black holes just from this part. So from this part of the signal, you can extract that the two masses must be 33.6 and 32.2 solar mass. By the way, very close to the first signal detected. And then you say, now let me use all the predictions of general relativity, the fact that they should create a Kerr black hole, that combining analytical and numerical information can predict from the knowledge of the two original masses what will be the mass of the final black hole you create and of its spin. The two original black holes are not rotating on themselves. They are just black holes that do not spin on themselves. But when you take two black holes like this and they coalesce, they will have the spin just from the orbital motion. So the final black hole will have a rather high spin. And this is what you compute here. You said that the final black hole should have a mass of 62.7 and a spin equal to 0.68 in some units. Now, the alert listener will have noticed that if I make the sum of 33.6 and 32.7, I get 65.8, okay, which is substantially more than 62.7. But this is normal because, as we had understood and said before, during the coalescence and just before, during the process, you lose a lot of energy to infinity, okay? A lot, but not so much a lot, actually, because you lose, you know, from 65.8 to 62.7, okay? You lose a small amount, but fractionally small, but not negligible amount, okay? And now, knowing these two things, you take the solution discovered by Roy Kerr from Cambridge in 1963, and then you can compute what are the modes of vibration of a black hole with these things, and then you ask, can I find these modes of vibration here? Can I check that this part is precisely the type of mode of vibrations predicted by this, okay? And also, you can check, but you can check by eye, actually, that Hawking's celebrated area theorem, which says that the area of, when you make the coalescence of two black holes, which have an area of the horizon of area 1, area 2, and they make a bigger black hole, that the area of the final black hole should be larger than the sum of the areas of the two black holes. Actually, that you can check by eye because the area is proportional to the square of the mass, and as the fractional loss of energy is just 7%, it's like making you know, the square of 1 plus 1, 2 minus 7% square compared to 1 square plus 1 square. So you compare 4 to 2. So it's a very nice thing, but not super accurate. Now, numbers, just here. So what is important in this? So these are two recent papers that have been published 2 months ago. I mean, I'm not sure the second one is published. I did not check. The first one for sure. And then I will not enter into the details, but this thing is a plot which says that the signal after the merger is a superposition of damped vibrations, so something which is exponential minus I omega t, where omega is a complex frequency. So you both have something which oscillates and something which decays exponentially. And what is important is one could see 3 different modes of vibration. So it's the first time that you have seen that the final black hole contains 3 modes of vibration, which all agree with what is predicted by general relativity from the knowledge of the initial system, okay? And you also check that the square of the mass of the final black hole is larger than the sum of the squares of the system, which is Hawking's area theorem, and this is checked here in this signal. But I want to cite another number, which is, you can do these tests in many ways, depending on various assumptions. But now, if you want to use all the information in the signal, one way to use all the information is not to say, I will use only this part of the signal and compare it to this one, is to say, I take this full signal, and then in it, by hand, I say, let's assume that one of the quasi-normal modes is not exactly what is predicted by general relativity, but differs by a fractional number that I don't know. And then you do the fit. And you can do that by using the analytical method, okay, I was mentioning. And then when you do that, you find that the fractional change in the frequency and the damping time of the loudest vibration mode cannot be larger than 2%, okay. I'm saying this because it's the first time that you have a 2% check that the solution found by Roy Kerr really describes black holes, and that we have seen a vibrating black hole with the 2% accuracy. You know, it's completely different from other tests of existence of black hole. And like for instance, other tests of GR is in cosmology, there are many things you can say about cosmology. I will not describe them. Let me mention, linked to the Nobel Prize given to Roger Penrose, Richard Genzel, and Gaze, Andrea Gaze, is at the center of our galaxy. There is an object that we don't see, but around this object there are stars going around. And by studying these stars for years, actually, one could check the periastron precession predicted by general relativity for this star. But this is like a 20% check of GR. And then the Event Horizon Telescope has given a direct image of a black hole at the center of our galaxy, or at least of what is around the black hole, and in M87, which are qualitative tests of general relativity, but from the quantitative point of view, they are not super accurate. Just to end, so the central message is general relativity have been developed for a long time and has been compared to experiment and is accurate, extremely accurate. But still, I want to end by saying there are two observational black clouds, that is to say, things that can be incorporated in general relativity if you assume that there is dark matter in the galaxy and dark energy in the universe. But we don't understand what is dark matter and dark energy. So is this a concern for the future? Other puzzles are at the theoretical level. When you combine general relativity with quantum mechanics, we know that something will go strange when you go to very small length scales. As Jacob Bekenstein and Stephen Hawking have understood, one should attribute a temperature to a black hole. A black hole should not be black, but as Stephen said in his first paper, black holes are white hot. You know, they emit by quantum effects. And then there are puzzles about what happens when the black hole fully evaporates. We should also remember, this is Slava Bukhanov, Chibisov died, that the fluctuations we see in cosmology are of quantum origin, which means that actually the origin of all our big classical universe is quantum. So we have to keep this in mind. And the conclusions is just this citation of Steven Weinberg, which illustrates what I said in the first part of my talk, is that sometimes people complain that theoretical physicists believe too much in theories. But as Steven Weinberg noticed, our mistake is not that we take our theories too seriously, but that we do not take them seriously enough. And the idea of black holes, for instance, is a case in point. For years, the theory said, I want to be there, I want to exist, and it took a very long time to take it seriously. Young-Mills theory also was discovered by Oscar Klein, by Pauli, and rejected, and things like that. And it is, and I fully agree with Steven Weinberg, it is always hard to realize that the numbers and equations we play with at our desk have something to do with the real world. It's the strange, beautiful feature of physics that we have equations, we have the world, and there is a match. Okay, thank you.
Thank you very much, Thibault. That was a truly inspirational talk. So it's really impressive how the recent observations are confirming general relativity to ever more impressive accuracy. So we have a few minutes if anyone would like to ask questions. So any questions? Martin.
Well, first of all, thank you for a really nice talk. Hi. I have a question about the binary pulsars testing strong coupling gravity. So, I mean, if I understand it correctly, you're saying I mean, I guess there are two ways one could look at it. One has a rather weakly bound orbit where the speed of, compared to the speed of light is sort of a figure of merit of how close, how one is to strong coupling. And then with the neutron star, you talk about I guess, something like the dimensionless potential on the surface. So could one imagine two theories that are very different near the surface, but that radiate the same way? Or I'm not quite convinced that one is really testing strong coupling gravity.
Yes. This is why, to prove this point, okay, we, with Gilles Esposito-Faez, we had shown that there exist classes of well-behaved theories where you just augment general relativity by one scalar field, which in the weak field limit and the solar system can be as close as you want to general relativity, 10 to the minus 100, or whatever. And then, and they have positive energy and everything is okay. And then in binary pulsars, they developed strong field effects due to the existence of the scalar degrees of freedom, and they predict deviations of the order of 50% in binary pulsar. So it's just a proof. It's not the proof that this is excluding all theories, okay? Definitely there exist theories that are different from GR and explain things, okay? But you have to screen away effects that could show up in other theories. So I hope it clarifies the question.
Any more questions?
Joe has a question. No.
Oh, sorry.
It was a wonderful talk, by the way. Sorry, a bit more of a general question. What's your sort of generalized opinion on the physics A-level setting you up for kind of a physics degree at like Oxbridge or Durham? Sorry, it's very general.
Sorry, well, so what is the question? I know nothing about the educational system in England.
Have you got any opinion on how much you feel that the physics A-level would set you up for a physics degree?
You are better to answer this question.
Maybe better to ask someone after the talk, because it's probably not quite. Well, Thibault knows a lot about physics, but maybe not about the not about the physics A level.
One important thing to keep in mind. Let me tell you what happened to Yvonne Choquet-Bruat. She wanted to solve this very difficult problem that I mentioned, that she was the first one to solve. She went to a PhD advisor, who was a famous scientist, Lishnerovitz, and then he told her, this is too difficult for a beginning scientist. So, but she did it, okay? So don't be afraid if somebody tells you you are not good enough for physics or science, don't believe this. If you want to do physics, do it.
Hi, thanks. Very brief question. You mentioned Hooke's law a couple of times in the talk, something like the gravitational memory effect. Is that also, can you also understand that in analogy as you mentioned the string that remains deformed after having stretched it? Is the memory law something similar?
Yes, indeed, Einstein's theory is beyond the linear level, so there are non-local effects in time, like in Hooke's law, where you need to end and non-linear and things like that. So anyway, it's just a way to open your mind. Yes.
This isn't a particularly technical question, but I was just curious, the slide just before where you mentioned the inconsistencies with other parts of physics, such as quantum mechanics, such as the fact that gravity isn't renormalizable. Because there's so much accurate experimental evidence that general relativity might be the correct theory, do you believe, do you think that it's quantum mechanics that will need changing in order to be consistent with general relativity?
No, I believe that string theory is giving us, string theory is a case in point of Steven Weinberg's thing, okay? Now people say, string theory, we have seen no evidence for it. There is so much evidence internally from theoretical physics that it is pointing to the good direction towards a theory that mixes quantum theory and general. And what is remarkable is the magic of string theory is you start from a string in flat space-time, string or a membrane in flat space-time, and then you get general relativity out of this without ever assuming that you know something about curved space-time or whatever. But experimentally, it also suggests that deviations, due to quantum mechanics are probably not very far from the Planck scale, different but not very far, which makes it, in my opinion, very improbable that LIGO-type physics will see deviations due to quantum effects, okay? And I would be happy if somebody like Kumar Vafa would be correct, saying that if you go at the millimeter micron scale, maybe you could have extra dimensions and things like that, but okay, but not at the 10-kilometer scale, okay? Sorry, but I would love to be wrong, that is to say. It is frustrating that general relativity is, alas, so accurate a description of gravity. I also hope that one would see deviations. Yeah, I should, let me know, because I worked a lot on this. I said that now we know that all bodies fall with the same acceleration to 1 part in 10 to the 15. But actually, I had worked both with Sasha Polyakov and with Gabriele Veneziano to invent models motivated by string theory, in which you could have no deviations up down to 10 minus 15, and then you would have deviations of the universality of free fall at 10 minus 17, 18, or whatever. In my opinion, it's still a possibility, and the window for me, which would be most important experimentally to see deviations, would be testing the equivalence principle at 10 minus 17, 10 minus 18 accuracy. And there, maybe if some dilatonic field is still long range, you would see something.
Okay, I think we have to get Thibault to his dinner, so I think that's a good place to stop. So please join me in thanking Thibault again for a fascinating, inspirational talk.